of the vector space, I'll call it P bar, so this is the complement. This means the complement of P. And we call its elements of giving all solutions which are not elements of P, and we call these elements negative frequency modes. And the space of classical solutions time code integration we call it S, and it's just a direct sum of P and P bar. Okay. Any solution can be written as a sum of an element of P and an element of P bar. Okay. Now let's build the Hilbert space. Well, first of all, we'll look at the vacuum state. So the so-called Minkowski vacuum state is defined by it's the state which is annihilated by all annihilation operators A. So this is our definition of Minkowski vacuum state. So the A case and the A case dagger are annihilation and creation operators. So I'm calling them operators, not operator value distributions. I am pedantic up to a point. It's not going to affect, we're going to ignore, I want you to be aware of that, but we're going to ignore it for most of the time. So annihilation and creation operators of a particle or quantum of momentum K. We can do as we did for the harmonic oscillator. We can apply the creation operators onto M and build particle states. So this is the state of a one particle of momentum K. And so for different Ks we have a space of one particle states. do this, you can put together all these states, all these one particle states with different momentum. This is the basis for the one particle Hilbert space equation.
Is it obvious that there is such a thing as the vacuum state? Can one prove that there is such a thing?
I mean, that's the definition. So, how could you not exist then? Like this is literally the definition of it.
So I always feel that in quantum field theory, the concept of the vacuum state is fundamental.
Is what?
It's fundamental. But I would imagine one can show that there is a sort of minimal energy level and that postulates that you can build everything on top of that minimum energy level.
Okay. So one thing we're going to do, the main thing we're going to do, the main point in the whole course is to destroy that.
That idea.
That idea. So, certainly in core space then, if what you mean, so such a state exists, this is my definition of state. Another question was whether it's a vacuum state, whether it's a state of minimum energy. So we'll see now in a second that it is a vacuum state. So, in fact, I never use the word vacuum. So you can ignore this view. Let's call it the Minkowski state. Now it is going to be a vacuum state for certain types of observers, inertial observers. So that makes it a privileged quantum state. Because inertial observers do see it as a vacuum state. But it's not a unique vacuum state. So I avoid the word vacuum state. I mean, sometimes I wrote it down here, but it is defined as a state like this. Whether it's a vacuum state or not, that's going to be the main thing in the whole course. And we'll see that in some sense it is, but not in all sense. It's a vacuum state in the sense that it's annihilated by this A case, but you could have other B case. That's why I said that decomposition of the field that I did at the start is not unique. You could decompose it in a different way, and so have different Fourier modes, Fourier coefficients. You can have different Fourier modes, therefore have different Fourier coefficients. And you could define the state which is annihilated with respect to those coefficients, and that would give you another vacuum state. It would certainly give you another quantum state. In general, it will give you another quantum state. Not necessarily different, but in principle, it doesn't have to be the same. And it can be a vacuum state with respect to certain observers or things in a certain way. I call it vacuum just equine harmonic oscillator, if you wish. We're going to get in depth in this. That's the root of the on-group effect in flat space. Okay, so we've got the vacuum state or the zero particle state in this sense with respect to this choice of it really is a choice of time that really, it's the T, it's the Cartesian T, it's the choice of Cartesian T that gives you those mode solutions, that gives you those Fourier coefficients, that gives you this vacuum state. And so, an observer that has T as its proper time will really see this as a vacuum state. But we're going to see this properly later on. I didn't really want to get into this. So with respect to this choice of bases, with respect to these bases, with respect to these UKs, we've got these Fourier coefficients, AKs. And with respect to those AKs, then can we find, let's call it vacuum state with respect to those in that choice. Okay? We've got the zero particle state. We can build one particle states in this way. Two particle states, three particle states, and so on. So the Hilbert space of the field theory, of the quantum field theory, is this is a curve in F. It's called the Fock space. It's the Fock construction of your Hilbert space. And it is complex numbers. That space of complex numbers, all it is, it's isomorphic to the zero particle state. So if they are isomorphic, they're the same states. It is the zero particle state. The state, the Hilbert space, this is isomorphic to the Hilbert space the space spanned by L, by the vacuum state. The zero is the zero particle space. And then you've got the direct sum. I wrote this symbol earlier on, which is the direct sum. And then you've got the one particle space, we just see how it's built. And now we need the two particle space, but this is bosonic. It's a bosonic field, so we need to symmetrize this. So this is H1 tensor product. So that in order to build a tensor, in order to be able to build the two particle state, we need to do the tensor product of one particle states, and because so this is the two particle state space, and we need to symmetrize this. So really, it's by this I mean it's symmetric tensor product. And this is because of the bosonic, it's a bosonic field. If you had fermion, you would have to antisymmetrize it.
Is this called H2?
Sorry?
Is this called H2? Doesn't have
I'm saying it was H2, but if you would define H2. I think H2, you see, I think H2 I think H2 really is, it would be creating two particles here with the same K. So I wouldn't call it H2. you can follow two paths building this, but that really is the correct path. You know, you could keep putting, instead of doing this, you can keep putting more particles, kth particles in here, and then, you know, increment the number of particles of k momentum, and then change the momentum. The different momentums for multi-particle states. Here we're doing the opposite. We're changing k, and then we're building up. So, well, keep going. H1, 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 synchronized, and teachers goes on up to infinity. Okay, so this is your Hilbert space of the full field theory. Okay, so now note there's a one-to-one mapping. So this object, this bra with phi, gives you a one-to-one mapping between H1 and the space of positive frequency solutions, the Klein-Bordel equation. So suppose that you've got an F tilde, which is an element of H1. It's a one particle state. And you write this as a linear combination of the bases of these bases here. Okay, this is a general element of H1. You write this linear combination of these bases. And this is mapped on to positive frequency solutions, P. So in what way? Well, in the obvious way of taking the expectation value. So, or dealing with primes and cats. So this is M phi x F2. The map of this, you define it as this way. Okay, now that's, if you actually do the calculation, that's the reason for this, for calling it this definition. Of the map and phi is this notation, if you wish, notation is that if you take if you now calculate this with phi expressed using the decomposition that we gave, so it's So this is just I'm just expressing the field in the mode composition that we did at the start. You can view as A and A dagger acting on F tilde, but we don't know how they act on F tilde. Instead of that, you can view as A and A dagger acting on M. Now, this tells you, if you take the adjoint of this, that tells you that M A dagger is equal to 0. And so A dagger acting on M is just 0. So this guy goes away. A dagger M A dagger is equal to 0. Okay, so that's so now I'm just expressing F, now I'm using this, expressing F as a linear combination of the bases. And this is just I should have defined the inner product first, but I'll do this in a second now. This is just K minus K private, which is just this. I forgot, I've filled that little space and I still didn't say what the inner product is. So in H1, we have the standard inner product in H1. So what do we mean by the standard one? It takes pairs of elements of the one particle hyperspace in here. I'm ignoring. You can I might alternate between being pedantic and not being pedantic. Okay, you can recover the fact that these are operator value distributions, and really you have an operator. Multi-operator acting there. A lot of times people just ignore this, okay? And a lot of times I will ignore this. This really is not C, but a distribution. But anyway, so this takes a pair of elements of H1, and it gives you this. this is where f is just written in that way. And G is written in a similar way. This is really the definition of the K-Tilde and G-Tilde case. Okay, so this is your inner product. And so you apply this to the elements of the basis. So in particular, the inner product of elements of the basis. You just apply the commutation relation now. So A dagger is 1 plus A dagger. A So the unit operator, first of all, the distribution, you just take it outside. The one is just the unit operator, which just returns the state upon which it acts. And then the other one is just 0, because this annihilates M, and this annihilates M to the left as well. So you just get and this is what they used here. Should have done the inner product earlier on. This for the inner product in H1, we're going to look for inner product in P in the next lecture. Any questions about this? Anything? Okay. In 2 weeks I won't be able to do the lecture, so we'll have to reschedule the lecture. So I'm going to ask you next week to look for times for the following week, between Wednesday. Okay. Whichever time, if you can make it or whatever time we decide, I'm going to put it up on the website that I gave the first day to say to which day we're scheduled. We will decide next week, we'll decide to which day we're schedule the lecture in 2 weeks.